and quantum systems, please.
Okay, so many thanks for this kind invitation. So it's a great pleasure to talk to you about the basics of polynomial optimization. So who in the room never heard about polynomial optimization? Okay, so then I will try to stay to be as basic as possible, and don't hesitate to interrupt me with questions. So I prefer to spend all the time on the 3 or 4 slides, but have interactions rather than just, you know, horrifying you with the whole bunch of things. Okay, so is my mouse work? Yes. Okay, so first I'm gonna start to recall what a polynomial optimization problem is. So basically, it's an optimization problem where the objective function is a polynomial, and all the constraints are defined by polynomial inequalities. So so basically, in dimension 2, I have a vector of variables, x1, x2. Can you see when I write? Okay, and so maybe the easiest nonlinear polynomial I can think about is f equal x1 times x2, and then if you think about the constraints, so maybe we can take also something very simple. So for instance, the constraint set is the unit box, and then so you can describe this box as the bunch of variables satisfying these inequalities. Okay, so each xi must be between 0 and 1, and this you have many ways to encode it, but this is one way with a degree 2 polynomial. Okay, and for simplicity, I will assume that the set of constraints is compact because everything is easier to explain, but many things also work in the non-compact. Yes? Sorry to interrupt, but we cannot see your slides. Wonderful.
Est-ce que tu as partagé ta fenêtre?
Yes.
Share your screen.
It is shared. Il y a marqué vous êtes en train de partager votre écran. Je vais arrêter le partage.
Pour le coup, ça avait l'air de marcher.
Ok, j'ai arrêté le partage, je vais remettre le partage.
Ah, c'est ceux qui voient ça. Voilà.
Okay, can you see my slides again? Yes. Okay, and if I try to write, does it still work? Or? Yes, wonderful. Okay, so yeah, so I suppose that everything is compact, and then the infimum is a minimum, right? And yeah, but a lot of things also work when you assume non-compactness. But very often in applications, everything in compact, the set of constraints is given, is quite simple, or not simple, or maybe non-convex. And in application, very often, all your input are sparse. So I will explain a bit later what I mean by sparse. But if you are very bored after 5 minutes, the next 5 minutes, then at least you can try to remember what is written here. So we use the notion of so-called correlative sparsity. So it means that you don't multiply all the variables to each other. And so here is a simple example of correlative sparse polynomial optimization, where basically you have a chain of links between the variables. So x1 is linked to x2, and x2 is linked to x3, but x1 is not directly linked to x3. And in many applications, you actually have a structure like that you can exploit to speed up the optimization. And there is also the notion of term sparsity. I won't talk about it today, but it's more widely used in systems of polynomial equations. And so it's basically when you have a very few amount of terms among the whole possible bunch of terms. So here I took an example in dimension 2. The degree is huge, it's like 101, but you only have 2 terms out of many possible ones. Any questions on that? Okay, I will try to go to the next slide. Again, so this is how we usually motivate the study of these problems. Because so these polynomial optimization problems, and in particular the sparse ones, they are everywhere. So you have them in deep learning applications, in power system applications, in quantum info applications. So I will try to spend a bit of time on the 2 latter applications. Okay, so this was the official advertisement. And before talking concretely about polynomial optimization, I will spend a few minutes to talk about linear optimization and semi-definite optimization. So again, I'm going to ask, who never heard about linear programming? Ah, okay. So you already know this stuff, right? So this is very basic. So here the objective function is just a linear function. And you have linear inequalities, so linear scalar inequalities. And the feasible set of such a problem is called polyhedron, or polyhedra. I always forget what is what, if one is infinite or not. But here, basically, we're going to assume that everything is compact and closed, so closed. And so this is linear programming, right? And then you can go to something slightly more complicated, that is semi-definite programming. So who never heard about that? Okay, so if you think about linear programming, then you will just replace the set of linear inequality constraints by linear matrix inequality constraints. So semi-definite programming will include basically all the linear programs, but also allow to handle a lot of other problems. So here this weird greater or equal, the sucsec, means that the difference of the two matrices needs to have non-negative eigenvalues. So is it clear? And so the unknown are the zi's. So these are your optimization variables. And you know the matrix is fi. Okay, so and then actually this feasible set is complicated. It's non-linear, right? But it's convex. And then there are efficient algorithms to do this kind of optimization. And actually, you can also add linear equalities or linear inequalities, and it will still be a semi-definite program. And now that I defined linear and semi-definite programming, now I can try to convince you that you can approximate the solution of a polynomial optimization problem with a sequence of semi-definite programs. And the first thing is a basic trick. So the initial problem, the one that you see above, is where is my, oh, okay. So is this one, right? So this problem is non-linear, but the set of constraints is finite dimensional, okay? And so the trick that we use is that we transform this non-linear problem as a linear problem. So it's an infinite dimensional linear program. And the decision variables are probability measures. So they live in an infinite dimensional space. And they are supported on the set of constraints. And actually, this minimum here is equal to the minimum of f. So does anyone see why? Like, does it seem obvious to you or not? Okay, so actually it's maybe not obvious, but it's not very hard to prove, so then I will do the proof with you, okay? So you need to prove two directions, right? So let's prove the first one. So the set of constraints is compact, then there exists a global minimizer. So I'm going to call x a global minimizer of f. So basically f of x is equal to f min. Okay. And then I will define the Dirac measure supported at x. So all the mass of this probability measure is concentrated at x. So I'm going to call that delta x. I don't know if this is standard notation for you. And then I'm going to integrate f with respect to this measure. But this is f of x, right? So this is f min. So delta x is feasible for the optimization problem over measures because this is a probability measure. And then it means that the minimum over all measures is less than this precise integral, right? So we proved one direction. So let's prove the other direction. So for the other direction, so you can just say that you know that f is greater than f min by definition of the minimum. And then we're going to integrate with respect to any measure. So then we obtain f d mu greater than f min d mu. But f min is a constant, and then you just put it out of this integral, and this is equal to f min integral of d mu. And since mu is a probability measure, this is equal to f min. Okay? And this is true for every measure, so this is also true for the minimum over all measures. And so this is the second direction. Any questions on that? This wonderful proof? So, okay, so then it means that you can actually transform the nonlinear finite dimensional problem into a linear infinite dimensional problem. So it's completely useless, right? Because you don't know how to solve the infinite dimensional linear program. But then we will see how to approximate it quite efficiently. And so here I wrote the dual. So the dual problem is a problem over non-negative functions. And so you have a pair of primal dual optimization problems. Okay? Who never heard about duality in optimization? Okay, perfect. Okay. So then we're going to see how to relax this complicated problem into a sequence of less complicated problems. So when you have a probability measure, then you can define the moments. So the moments are the integrals of the monomials. So here I will, for simplicity, take an example in dimension 2. So I have again x equal x1, x2. And then, for instance, I want to integrate x1, x2. So I have two variables, and then I will have two indices. So this, I will call this y11. So the first one corresponds to x1, and the second to x2. Similarly, I can integrate x1 squared. So there is no x2, so it's x2 power 0. And x1 is squared, so then I put a 2 here and a 0 here. Is it clear, this notation for the moment sequences? Okay. And so actually, so you can basically integrate monomials, but you can also integrate polynomials. This is just the sum, right? So for instance, if I want to integrate x1, x2 plus 2 x1 squared, so this is y11 plus 2 y20. Okay, so then I can do that for any polynomial. And so actually, the basic idea behind this hierarchy is that you're going to linearize everything as if you would integrate all the nonlinear terms. Okay, so for every nonlinear monomial, you're going to associate an additional variable to your optimization problem. And this optimization variable will be the y alpha. And this y alpha, you can put them in a matrix. So you can fill a matrix with them. And we will see after why it's interesting. And this matrix is called the moment matrix because it's full of moments. Okay? And so the way you fill the matrix with moments is that you index the matrix by all the monomials. So here, for simplicity, I only took one x1, x2, but then you could also add x1 squared, x1, x2, x2 squared, and so on. And to decide which entry, which moment you put, you multiply the row, the column index by the row index. So here I multiply these two guys. So this is x1. And I put the corresponding moment entry. So the corresponding moment entry is y10, so this guy. Okay? And so for instance, if I multiply x1 by x1, I have x1 squared. And then it gives me y20. Okay? So this matrix depends linearly on y. So basically, if I have some non-negative eigenvalue constraints on this matrix, it is a semi-definite programming constraint, right? And what is nice with this matrices is that they have non-negative eigenvalues. Okay, so this is the key idea. So why is that? Do I have time for this proof? Yes. Well, what does it mean to to have non-negative eigenvalues? Well, it means that if you take a vector of coefficients with the right size, the same as the size of the matrix, well, it should be non-negative, right? And actually, it's not very hard to prove that this thing is actually equal to the integrals of a polynomials built from this coefficient. And since mu is a probability measure, then this is non-negative. So this is how we prove it. So I think I will not have time to do that, but this is the general idea. And so basically, you take any polynomials, you write it like that. So it's the sum of the coefficients multiplied by the monomials. And then you basically take all this sequence P alpha, and this is my P overlined. So this is to make a distinction between the polynomial itself and its vector of coefficients. And actually, it's not very hard to see that this integral is precisely equal to this, because it contains the y alpha plus beta, and then so you have to take the square of the polynomial. So you also have the alpha plus beta appearing. Any questions on that? Okay, and you can do the same for the constraints. So for the polynomials defining the constraints, so you can build a so-called localizing matrix, but I will not bother you with the definition of this. And it also has these nice properties that has non-negative eigenvalues. Okay, so if you have a measure, then you have this. You must have this. So these are necessary conditions. And so this is how we relax the initial problem. So the problem that you see on the left, we relax it like that. So we linearize all the x power alpha, we replace them by the y alpha. And then we impose that this moment matrices must be PSD, so semi-definite positive. Any questions on that? Oh, and y0 equal 1 is because you have a probability measure. So the integral of d mu of 1 times d mu should be 1. Okay, so and then the motivation of using sparsity is because this moment matrix that I displayed earlier it grows quite quickly when the number of variables and the degree of the polynomials increase. So that's why we try to exploit sparsity to fight against this problem. So this number here, it's the dimension of the vector space of polynomial depending on x1 up to xn with degree r. Is it clear for everyone? Like, have you ever seen this proof somewhere? Or? Yes, no? In the univariate case, is it clear? So in the univariate case, it's n plus 1 n. So it's n plus 1. No, sorry. One plus r, 1. So it's r plus 1. So it's the dimension of degree r polynomials in one variable. Okay, and so you can generalize this to any dimension. So this number grows quite quickly. Okay, and then I'm going to spend a few minutes talking about the dual of the moment problem. So how much time do I have left?
10 minutes. He started at 1:45.
Okay, so I talked about probabilities and moment sequences, and there is a dual side of the coin that is by means of sum of squares multipliers. So the general idea is the following. So you have non-negative polynomial inequalities. They are too hard to be handled, and then you're going to replace them by sum of squares constraints. And so this, you can handle it with convex programming, semi-definite programming, and so on. So the general idea is as follows. So I took my, my stupid polynomial f equal x1, x2, and I took the box. And then, so what I want to do is that I want to express f as a sum of squares combination. So what does it mean? It means that here I have a constant. Okay, so I will talk later about this constant. And then here I have a square. So this is what it is. So a square of degree 2. Here I also have a square. And here I also have a square. So squares and sum of squares are non-negative everywhere, right? And here I put the polynomials that I use to define my constraints. So by definition, this guy is non-negative on the box. And same for this guy. So it means that the whole sum here is non-negative on the box. So it means that f is greater than minus 1/8 on the box. Okay, so then you will say, hey, but we know the minimum of f on the box, right? So what is the minimum of f on the box? 0, exactly. So minus 1/8 is a lower bound of 0, so a lower bound of the minimum of f, okay? And so why is it not very accurate? It's because I considered sum of squares of degree 2. So if you want to get more, you need to increase the degree of the sum of squares. So you need to take degree 4 for this guy, degree 2 for this guy, degree 2 for this guy, and so on and so on. And so that's how you obtain a hierarchy. And so here I cheated, I put coefficients of the sum of squares, but in general you don't know them, but you can compute them with semi-definite programming. Any question on this? Okay, so in the few minutes, so this is a recap. So I showed you the moment side on the left, the dual SOS side on the right. And then I will quickly explain how you derive sparse variants, but that will be extremely basic. So before talking about sparse polynomials, I will talk about sparse matrices. So basically, so if you have a symmetric matrix, you can index it by graph vertices. So you can say that the support of a matrix is a graph. So what does it mean to be supported by a graph? It means that so you connect your graph with edges. And so for instance, here I have no edge between 1 and 3. So in this matrix indexed by the graph vertices, here I have 0. Right? Okay. And we will use the notion of chordal graph. So who doesn't know what a chordal graph is? Don't be shy. Okay, so a chordal graph is a graph where whenever you have a cycle of length greater than 4, there must be a chord. Okay? So for instance, this guy here is not chordal, because there is no chord here and there is no chord here. But hey, it's easy to make it chordal. You can just add chords, right? So here I put a chord here, but you could also put a chord here. So the chordal, this is called the chordal extension. So you can make any non-chordal graph chordal, but there are many ways to do it. And so yeah, this is what I explained here. And so the nice thing with chordal graphs is that you can easily compute the maximal clicks. And we're going to use that, we use that for sparse polynomial problems. And so to draw an analogy, so when you have a sparse polynomial, then you can build a graph. So you have a bunch of vertices corresponding to the variables. And same as for matrices. As soon as you have a multiplication, then you put an edge. So for instance here, x4, that is represented by this node, is only multiplied to x1. So there is only an edge, an outgoing edge from 4 to 1. So this graph is kind of sparse. And actually, so this graph is not chordal, because there is, at the beginning, there is no chord, no direct chord between 3 and 5. But then, same, you can make it chordal, so you can add an edge here, right? And then, well, as for the matrix case, you can compute the maximal clicks. And the very basic idea of sparse polynomial optimization is that instead of considering x1, x6, then you will just consider the subsets of variables corresponding to these clicks. Okay? And these kind of problems appear in for the graph modeling the electrical network. So this is used by the French transmission operators. This kind of sparsity also appear in quantum information theory when you look at Bell inequalities. But I will not have time to talk about this. And I wanted to end the talk by saying that so these polynomial optimization techniques, they are a very powerful tool to model a wide range of problems. And you can build quite efficient approximation algorithms, and there are software to do all of this for you. And many applications in modern fields, so power energy and quantum information theory. And I wanted also to advertise the fact that we have many positions available in an Anity chair. So for those who don't know Anity, it's the Artificial Intelligence Center in Toulouse. And I will be happy to discuss about potential applications. And many thanks for your attention.
Hello everybody, and welcome and thank you for being here. So I will provide you with a very brief introduction to an old tool, which is called the Christoffel function. And I will try to convince you that this can be useful for some application in data analysis or data mining, and also has some connection with not so much expected actually. And also it's very interesting to see that this tool is very simple to use, no optimization involved, has a link with the presentation of Victor also. And of course it's not magic in the sense that it has you have to pay a price to use it, because there is some matrix to invert, but modulo the dimension of your problem, it has a lot of interesting properties. So I try to convince you about this. So anybody else already heard about the Christoffel-Darboux kernel or Christoffel function, or no? Okay. So most of the material, if you want to have more detail, is contained in this book. And so I will try to define briefly the Christoffel functions, some application in data analysis and connection, but I won't probably have time. But you can use the slides if you want to have more details. I will present only part of the slides, not all the slides. And if you want some links, you can just read at the slides and you will have some connections to literature and more details. Okay. So the two guys in the picture are, on the left is Christoffel, it's a German mathematician, and Darboux is a French one. And you see the picture below was done by Edward Powell, was professor here actually. And it's a dimension 2 picture where it was drawing a lot of points to mimic the C and the D of the Christoffel letter and the D letter. So you can do it yourself to play with the tool. You will see it's very easy. You generate points in the plane to make a picture. Like for example, this CD, but you could have enough point so you see a geometric shape appearing, okay? And the Christoffel function is this red line. I mean, this red line is precisely the level set of some function, which is called the Christoffel function. And you see the magic here is that this red line captures the shape of the cloud of points. Okay, and this is a story about the Christoffel function in data analysis, of course, which was not the primary goal of the people working in this area, because it's an old tool, as I said. It dates back to more than 100 years ago, and it's a tool that comes from a theory of orthogonal polynomials and an approximation theory. Okay. So I claim that these simple tools, I claim it is simple because you will see the computation is quite simple. There is a non-standard application of the CD kernel, Christoffel-Darboux kernel, which provide a simple, quite easy to use tool with no optimization involved, modulo the dimension. I don't claim that you can do the same thing with a large dimension, but which can help solve problems not only in data analysis, but also in approximation, interpolation, possibly discontinuous function. In particular, for the last case of interpolation, what is nice that in many cases you can approximate your function without what is called the Gibbs phenomenon, which is typical when you want to approximate a discontinuous function with a polynomial. In this case, you'll see the picture in the middle. You see this nasty function is quite well approximated by the Christoffel function with no Gibbs phenomenon. So how does it work? You'll see you can do it and play with this tool very easily on MATLAB. Okay, so you see this picture here. You could draw a bunch of, as I said, a bunch of points on the plane yourself. Enough point to make some geometric shape appearing. Like for example, here you have a T which is rotated. Okay, and as I said, you see this red curve on the picture is in fact, if you look at the red curve here, it's a sublevel set. I mean, the points which are inside the red curve is a level set of some polynomial, QD of x. Okay, so we are in dimension 2 here, and here there is a polynomial QD of x in two variables x1, x2 of degree d. Okay, and you see that if you look at the gamma is some value that I don't go into details how to choose this value, but if you look at the set of x in the plane that satisfy QD of x less than gamma, you retrieve all the points that you see inside the, and you see you capture very well the shape of your cloud of points. Okay, and this is not a coincidence. See, there are a bunch of examples in dimension 2 again, where you have different pictures. So I don't see the degree here, but the degree was not very high. So with a relatively small degree d, you can construct a polynomial like this one, QD of x. And when you draw the level set of this polynomial, you see that each time for this example, you capture quite well the shape of the cloud. Okay. So I'm not claiming that with a low degree you can do that in larger dimension. We don't know, but at least for dimension 2 or 3, or for data analysis in dimension 2 or 3 or 4, it seems that with a quite low degree d, you approximate quite well your shape of cloud, the shape of your cloud. Okay. So how do you compute this polynomial? You will see that it is quite simple. So here we are in dimension p equal 2. So p is the dimension here. We are in two variables. D will be the degree of your polynomial. Okay. And SD is just this scalar, which is, you have seen with the talk of Victor before, it's just the dimension of the vector space of polynomial of degree d in p variable. So when you fix d, you look at Vd of x is a vector of all monomials in two variables of degree d. So you have the constant term, the linear term x1, x2, the quadratic term x1 square, x1, x2, x2 square, etc., until the last one, which is x2 to the power d. Okay. So the length of this vector is precisely SD. Okay. Next step. Oh, sorry. Oh. Okay. Next step is, once you have this vector of monomials and you have your cloud of points, you are going to compute a matrix, a real symmetric matrix, which is very simple to compute. You take each point xi, you evaluate your monomial, your vector of monomial Vd at the point xi, and you multiply by, so you have Vd vector colon, you multiply by Vd, the same vector but the row vector, transpose. So when you multiply these two vectors, you get a square matrix, okay? And you do that for each point, and you add up and you divide by n, the number of points. So it's quite simple manipulation, okay? So what is this matrix? A real symmetric matrix of dimension S of D. And in fact, it's just what Victor was mentioning before in the talk it's called a moment matrix, and it's a moment matrix of what measure? There is a measure behind that, and the measure behind that is quite simple. It's just the empirical measure supported on the cloud of points. So mu n is just the sum of the Dirac measure at the point xi. You take the sum of over all points and you divide by n, so you get a probability measure. Okay, it's a discrete measure which is supported on the cloud of points. And this matrix here, MD, is just the moment matrix of this measure. Okay. So you see the computation is quite simple. And we have seen again with the talk by Victor that if you, for example, for degree 1, what is the moment matrix of a measure mu? If you have a measure mu in two variables, and then you will look at the moment matrix of degree 1, M1 of mu. So it's the row and columns are indexed by the monomials of degree up to 1, so the constant term and the linear terms here. And then you fill up the entries exactly as Victor was mentioning before. Okay? So computing this matrix is just doing, with the empirical measure mu, it is done exactly as we have seen in the previous slide. Next, how do we compute this polynomial QD of x that we have seen in the picture? Then it's very simple. Once you have your matrix, the moment matrix associated with the empirical measure mu n, you have the moment matrix MD of mu n. So you take the inverse of this matrix, and you multiply on the left by the vector Vd of x, and on the right by Vd of x. See? Again, very simple manipulation. Simple modulo the fact that you have to invert your matrix, which is the case where if you have a large dimension, it could be problematic. But suppose that you can do it like in small dimension, it's very easy to do, especially if the degree d is not very high. So this is the only computation you have to do. So this is your, and this of course is a polynomial, which is a sum of square. Okay? So it's a polynomial in two variables, which is a sum of square of degree 2d. And now you look at, you plot the level set, the point in the plane, such that QD of x equal gamma. And this is a red curve we have seen before. Here, for example, see, when you put the point of x in the plane such that QD of x equal gamma, it's exactly the red line you see on the picture. So it captures the border, the boundary of the cloud of points. So that's all. That's a way to compute your polynomial. And what is the Christoffel function? So the Christoffel function is just 1 over this polynomial. Okay, it's a rational function, which is 1 over this polynomial. And as I said, there's a rich history in approximation theory and orthogonal polynomials. And many people in the area are those mathematicians. But they were not using it for data analysis the way I did it for a cloud of points. The idea is to start just a brief background on the Christoffel-Darboux kernel and the Christoffel function. They start from a set omega in RP, a compact set, and the measure mu whose support is exactly omega. So the starting point of the Christoffel-Darboux kernel. So they don't talk about a cloud of points and so on as I did. They start from a given set omega in RP, and a measure mu whose support is omega. And then they are going to construct a tool which is called the Christoffel-Darboux kernel and the Christoffel function associated with this set omega and this measure mu. So you start by defining the Hilbert space L2 of mu, the space of square integrable function with respect to mu, and then you consider the polynomial, the vector space of polynomial of degree d. Then you can see this vector space as a subspace of L2 of mu. Okay, and then this is called this vector space, finite dimensional, is called a reproducing kernel Hilbert space. Maybe you have heard about this reproducing kernel RKHS in machine learning. It's a very common word now in machine learning. And it's called a reproducing kernel. And what is this kernel? The Christoffel-Darboux kernel is just the sum of I forgot to mention before. Yeah. So given your measure mu and your set omega, then you can define a set of a family of polynomials P alpha, indexed by alpha, which are orthonormal with respect to mu. That's always possible if your moment matrix of mu is positive definite. So I don't go into many details. So don't go into details how to compute those p alphas. There is a way to compute those orthogonal polynomials. And you define the Christoffel-Darboux kernel very easily. So it's just the Christoffel-Darboux kernel associated with mu, n of degree d, is just the sum of all polynomial orthogonal with respect to mu, n of degree less than d, and you multiply p alpha of x by p alpha of y, and you make the sum. So this is called the Christoffel-Darboux kernel. And the Christoffel function is just, there are several ways of defining the Christoffel function. We have seen already one. I give you two others. So it's just the diagonal of the Christoffel-Darboux kernel. So it's just sigma of p alpha of psi square. So it's a function you can evaluate on the whole space Rp, right? And it's just to take the diagonal of the Christoffel-Darboux kernel. It has also a nice variational property. Okay. So it also, you can evaluate at a point psi the Christoffel function by minimizing, you solve a quadratic optimization problem, convex, where the idea is you want to find the polynomial of degree d that minimize the L2 norm of p, so you want to minimize p squared d mu, and you have the constraint that at the point psi in Rd, you want this polynomial to be equal to 1 when you evaluate at the point psi. And this is also another way to define the Christoffel function. Or, and we have seen that before in the slides, the inverse of the Christoffel function is just this moment matrix of mu. Take the inverse, multiply on the left by the vector of monomial up to degree d, and on the right by the same vector. So there are three ways of defining the Christoffel function. Okay. And now I come to the crucial point that will explain to you why you have this nice property of identifying the geometric shape of your cloud. There is one way to summarize this property, is that the Christoffel function associated with this measure mu, think about your empirical measure you saw at the beginning, identify the support omega of the measure. Why? So remember, we start from a set omega in Rp, and mu is supported on omega. The support of mu is exactly omega. Okay? And then, if you look at the Christoffel function, which is the Christoffel-Darboux kernel on the diagonal, since, remember, the Kd of xx is just this sum of square, sigma of p alpha of psi square, and you are going to fix psi. And you are going to look at the way this quantity grows when the degree d increase. Because when the degree d increases, you add more and more terms. So this is a positive function, the sum of square. And when the degree d increases, of course, the value increases. Okay? And the idea is to look at how does this increase looks like with the dimension and the degree. So, and this is the nice property of the Christoffel function. This increase has a dichotomy property depending on whether you evaluate your Christoffel function inside omega or outside omega. Okay? So when you evaluate the Christoffel function or the inverse of the Christoffel function k mu d of xx at a point psi which is inside the set omega, then the growth, you fix x in the set omega, and you look at k mu d of x when d increases. This growth is no more than polynomial in d. It's a polynomial in d. D to the power p. P is the dimension. Sorry. Whereas now, it's at most polynomial. So the increase is like a polynomial d to the power p, basically. And now, if you evaluate this Christoffel function outside omega, okay, now the growth is at least exponential. And this is this dichotomy that explains why this red curve captures the side of your cloud. Okay, so to summarize this property, look, for example, here I took an example where the set omega is this gray shape here. Okay, and basically the growth of your Christoffel function when you are inside So mu is a measure support on omega, okay? And when you evaluate the Christoffel function inside, okay, then the growth with the degree is no more than d to the power p. But if you evaluate outside, it's at least exponential in d. Okay, so why does it explain what we have seen before? Okay, so here the measure, the set omega is just this t rotated, right? And look at this set S gamma. You fix a d, say d sufficiently large, and you look at this level set. And remember, this is the inverse of the Christoffel function. So this k mu d of xx. So suppose you are not in the t rotated shape. You take a point x, which is in the take a point x somewhere here, for example. Take x here, and you evaluate qd of x. We have seen that qd of x, when you are outside, it grows very fast. And gamma is something like d to the power p. So if x is outside, it cannot satisfy qd of x less than gamma, because it would be exponential. It grows very fast, so it cannot be less than gamma at step d. Whereas if you take a point x in the black area here, for example, then since the growth in the degree is less than d to the power p, it will be contained in this set. It will satisfy qd of x less than gamma. That's all. So you see how this sample property, this dichotomy property of the behavior of the Christoffel function, depending on whether you are inside or you are outside, explain why this red curve identify somehow the boundary of your, not exactly, but roughly speaking, basically yes. Okay? Sample IDs, sample tool to use, rich theory behind. So it's a nice property, of course. So as I said, if you show this property to an expert in theory of approximation or orthogonal polynomials, of course he's not surprised, because he knows that from a long time. And the idea here is that surprisingly in low dimension with low degree you observe this, and you can use it for data analysis, whereas these mathematicians don't care about this problem. They were not interested in that. So I try to explain to you why it looks like magic, but people who are in the area, who know very well the Christoffel function, are not at all surprised by that. I was surprised when I saw it, because this happens with a low degree in a small dimension. I found that very interesting. And for data analysis, I think it is interesting. And if you're not interested in data analysis, you are just saying, oh, so what? Okay. There are some nice other property of the Christoffel function. will not go into details, but this is not the only property. But you have nice, more tricky property, and which require more sophisticated arguments to show, and some assumptions also. So, for example, when you scale your Christoffel function lambda mu d by this nice scalar s of d, and then you can show that the measure mu the measure nu with density, this rational function, converge to what is called the equilibrium measure. So it doesn't tell you anything, but just to mention that some property. Okay, and so that for data analysis, I will, as I said, one application we found interesting in data analysis is how to use this in data analysis. For example, detect outliers. Okay, how would you detect outliers? Suppose you have a bunch of so you have a bunch of data. Suppose you have a data in your data analysis problem. You have a cloud of points, and of course you would like to detect what are the points which are outliers. So for example, you clearly see that if you take a point here, it should be an outlier. it doesn't belong to the distribution mu, right? And the way to do it is just as I said, you pick up your score function, QD of x. You define your score function to be the Christoffel polynomial, and you decide that the point x that satisfies this will be inlier, they are okay, and the point x that violate this threshold, you will declare them to be outlier. That's a very simple way to use this Christoffel function for detection of outliers when you have a cloud of points. And I will mention another one briefly that we found also very interesting. That usually a classical way to approximate in approximation or interpolation, you want to approximate, let's say, a nasty function. Here, take the step function in red, a discontinuous function, and you want to approximate this function. So you assume that you know this function only by points somewhere. You don't know exactly of the function, and you would like to approximate it by a polynomial of degree n. When you do that with the classical way of using the Christoffel-Darboux, the standard way of using a Christoffel-Darboux kernel, you approximate your function blue f, in blue f, and in the picture it is red. You approximate it by your polynomial f hat of n of degree n. You will observe some, it's called this oscillation, which are not very nice. This is called the Gibbs effect. And that we claim that there is a way to avoid that by looking now, instead of looking at in the first approach, you consider the measure dx on 0, 1, okay? And this measure has nothing to do with your function. And you use the Christoffel-Darboux kernel to approximate f. Here we say something different. Instead of looking at the measure dx on 0, 1, a univariate measure, we consider the measure mu supported on the graph of the function. So now it's a measure in dimension 2, which is x and f of x, right? The set omega is just this set of points in 0, 1. So it's 0, 1 square, sorry. It's 2 dimension. And now you consider the measure phi, which is the marginal on x is just the indicator of the 0, 1. And given x, the conditional is just at the point f of x. So, yeah. So when you, when you do that, I'm not going to detail, but when you look at the Christoffel function of this two-dimensional measure, there is a way to approximate your function. So your approximate will be this point here. So you compute your Christoffel function associated with this measure phi. And then you fix x and you look at so this is a polynomial in degree of degree d in 2 variables, x and y. So when you fix x, now you look at the minimum in y. So it's a polynomial of 1 variable, sum of square. You look at the minimum, and this is what you call the approximation of f of x. And what is nice is that, you see, for example, in this case, you cannot see the difference between the approximand and the original function. And the shape of the function is quite bad, because it's discontinuous, and the same thing on the right, right? And this is why, in this case, you don't have this oscillation, the Gibbs phenomenon. So I think I will stop here, because there are many other applications, and I cannot describe all of them in some slides. I hope that you get some clue about this tool, which is, as I say, quite simple to use, but it has some nice other connection with many fields, and also other potential applications than just the one I just mentioned. Thank you very much.
Thank you very much. Other questions?
Yeah. Not really a question. Can you just explain how the dichotomy between if you are inside or outside of the level set, you explain with the property how we
The red label.
the shape
Yeah.
around T. Can you just explain this?
Yeah, because as I said, if you look at this set, sorry. Right, so here, yeah. So you have your cloud of points, right? From this you compute your QD of X, okay? And we know that this is a Christoffel function of the measure mu supported on the cloud, okay? So suppose D is somehow large, your degree D is large. We have seen that when you fix an X arbitrary in R2, sorry, well, in R2, in the plane here, depending on whether you are inside or outside, the QD of X will be very large. So if you are outside the support of the measure, QD of X will be very large. So it cannot be less than gamma. So if you fix gamma, the value was d to the power p actually. It was basically d squared. When you fix gamma like that, and you take a point x which is here, this cannot happen. So it will not be there. Whereas when you are inside, of course you satisfy this because you are in the support of your measure. So the value of QD of X will be less than gamma, so you are inside this, that's all.
Any questions? Not, there are no questions from the so let's thank the speakers again.
Thank you.
So the second talk of this afternoon will be given by Yohann GENZMER, and it will be about the Poincaré and inverse Poincaré problems.
So,
please.
Thank you very much for the invitation. So I hope everyone can hear me here well. And I try to write as big as I can on the blackboard so that at distance they can see what I wrote, what I'm writing. If ever you didn't manage to read what I wrote, please say something and I will write again, okay? Okay, so I will write down on the blackboard immediately the question that Poincaré addressed in 1988. So the question was the following. Given an ordinary complex differential equation of the following form. So this differential equation of the following form, it is write down p of x, y of x times y prime of x has to be equal to q of x, y of x. And in this equation, so x is a complex variable. Y of x is a function of the variable x. Let's write it down something like that. And p and q are a polynomial function. So this is important. They are polynomial function, right, of the variable, the complex variable x and y. And so what was the question that Poincaré asked? He asked, can we decide so I'm not going to explain very, very precisely what I mean by decide, but somehow during the talk we are going to have some idea of what I mean by to decide. So can we decide whether or not this equation has an algebraic solution? So actually in 1888 there was a contest organized by the King of Sweden, and the contest was about try to say something interesting about the stability of the solar system. And at this time, Poincaré published a paper where he studied this stability and said, at the end of the article, he said, yeah, the solar system is stable. A few months after, he realized that he made a mistake actually in his article, so that the solar system is actually unstable. But this mistake is very, very important from the historical point of view, because it was really the moment, the date of birth of a theory of dynamical system. And so the idea of being a system, differential system, for instance, the idea of being stable means having a periodic solution, which means more or less having a compact solution. And if you translate this idea of periodicity, of compacity into the world of algebraic geometry, then the question becomes more or less this one. If you reduce it in dimension, is the system such a differential equation, ordinary differential equation, as an algebraic solution? Here, algebraic refers to this idea of compacity or periodicity or stability. Okay, just to be sure, let me just say what means has an algebraic solution. This is the following. So you ask that there exists a function y of x, which is of course a solution, which is can be derivative, and as a derivative, that is a solution of this equation. And also, if you look at the graph x, yx, so the graph of this function, where x belongs to the domain of definition of y, this has to be included in the zero set of some polynomial function. Of some polynomial function. Okay. So the question is, if you, more or less the question is, if you give such a differential equation to a computer, can you find an algorithm that say, yes, there is an algebraic solution, or no, there is no algebraic solution? Of course, when Poincaré was studying this problem, there was absolutely no computer, so the question was not expressed this way, but this is more or less the idea. Okay, you see in this equation there is two variables, x and y somehow, but the variable y is a bit more privileged than the xy, because we look at the solution which is a function of x on the variable y. And actually there is no reason to make this kind of asymmetry. So to recover this symmetry, we are going to change a bit the object we are studying, and we are going to change it this way. So instead of considering, yeah?
So are you only interested in the question whether there exists a solution, or do you also want to be able to
find it?
To find it, or at least to have a way to...
Well, actually, this is more or less the same question. To be true, the answer is going to be no. So the problem is solved. Okay, so I'm going to transform a bit this expression. Just it's okay. Y prime of x, you can write this way, like a physicist, and even more, you can decide to divide by dy, like a physicist, and you get this relation. You can say this is minus equal 0, and you get a new object here. Remove the variables. You get what is called a vector field. Okay. So the object I'm going to study here in this talk are vector field on C2. So let X be a vector field on, let's say, a polynomial vector field on C2. And so you can write down this way. And these two guys, d over dx and d over dy, are the section of, well, you know that the vector field is a section of the tangent fiber bundle, and this fiber bundle on C2 is trivial. So more or less, I mean, to be very, very precise, these two guys are the section of the tangent bundle of C2, which is the C2 times C2, because this is trivial, and d over dx is the section defined by goes to alpha n 1, 0, and d over dy is the section which is defined by alpha goes to alpha 1, 0. Okay, this is just to precise the notation. So this is a vector field, and such a vector field can have a solution, or you can call this integral curve, or you can call this trajectories, or you can call even a leaf in the theory of foliation. But what is a solution? Or as I said, I like this word, a leaf or an integral curve. This is a many different way to speak about more or less the same object. So this is just a curve, let's say parameterized by some complex number z, which, so you have, the curve is parameterized like that. Okay, so this is a point in Z2. If you, so this drawing, this is the parameterization of some curve, and it is a solution of the vector field. It is a solution of the vector field if, when you evaluate x on the point gamma z, it is tangent to the velocity, the derivative of gamma. Okay. And of course, there is a dictionary which is more or less completely trivial between ordinary differential equation with solution and vector field with leaf, integral curve, solution, etc. The idea here is that with that point of view, you see that there is no privileged variable between x and y. There is this kind of symmetry, and this is much better for the theory. Okay, so let me give you the first example. So I'm going to start with the very simple vector field, but it's the first example. So I look at this, sorry, d over dx. So this is a linear vector field. So I'm going to make the whole computation for you. So this is a linear vector field. Linear meaning that there is just x and y and no power of x and y bigger than 1. And I here is the complex number. Yeah. Okay. So if you suppose that gamma z, we are going to look at the solution of this vector field. So if you look at gamma z, suppose that we are going to check for some solution that is written this way, z and yz. So we are going to start with solution such that the first coordinate here is just the variable z. So you can translate what means gamma x of gamma z being tangent to gamma prime. So if you compute the vector field on gamma z, yeah, this is just z and e y z, and gamma prime is just 1 and y prime. So this gamma is a solution if and only if y satisfies some differential equation. If and only if zy prime of z is equal to I y of z. So you have to solve this equation in the complex field, of course. So you can write down. So let me draw a picture here. So this is, let's say, the x-plane. And here you have the y direction, which is also a complex direction. Of course, I cannot draw a picture in 4 dimensions, so this is why you have here a c-plane and a y-plane, another c-plane which represents the y direction. Okay, so let's solve this equation. So you see this is immediate. You can write locally, the solutions are written this way. It's a constant time exponential of I log z, where this log z is some determination of the complex logarithm. Some determination of log z. Okay, and so yeah, there is some here integration constant. So if you put c equal to 0, you have a uniform solution, which is whose graph is the x-plane. So you have this, which is a whole solution. This is a uniform solution, which is defined everywhere on the complex plane. And now if you put c not equal to 0, let's say, for instance, c equal to 1, what happened here is that if you have your solution is, let's say, locally defined, for instance, fix x z here equal to 1, and around z equal to 1, your solution is locally defined. So here you have a small graph. This is the graph of the solution, a small part of the solution. And what you can do is, using the complex extension of the logarithm, you can turn around this point and make the analytic extension of the solution. So you turn around this way. Okay, you imagine like that, okay? And what is going to happen is that you are not going to go back exactly at the same level. I will try to draw something much better just after. But the explanation is that when you make one turn around z equal to 0, the determination of the logarithm is going to change by 2i pi. And so after one turn around, which I'm going to write it this way, meaning that you make the analytic continuation of the solution around z equal to 0, and you make one turn around z equal to 0. So this is the meaning of this notation. So you are not going to find exactly this expression, but this expression multiplied by, so you have to add 2i pi multiplied by I is equal to minus 2 pi. So actually you will find y of z multiplied by exponential of minus 2 pi. So, and of course you can do the same again and turn around the z equal to 0. And then what you see is that the picture of the other solution are look at like this. So let me try it. Some of my colleagues are very, very expert of pictures. So this is something like that. So here you and turn around, etc., etc. You have something more or less like that. You have a Riemann surfaces, so which is from the point of view of complex dimension, which is a curve, which turn around the y-axis infinite number of times. Of course, you can make the same computation. Here you see I started the computation by making the variable x, let's say, privileged. You can make exactly the same computation doing the opposite, saying like you look at some solution which written this way, x of z and z. And what you are going to see is that the whole y-axis is also a solution. And apart from that, you will recover the same solution that you find here. And so in this situation, already in this very simple example, you have two kinds of solution. First of all, you have the solution which are algebraic. There are only two algebraic solutions, which are actually the axis. Two algebraic solutions, which are x equal to 0 and y equal to 0. And all other solutions are not algebraic. And you can see it quite easily the following way. Why these Riemann surfaces or complex curve are not algebraic? Imagine that I draw this line, which would be the line x equal to 1. So it's easy to see that you are going to have, see, if you look at a solution which is not x equal to 0 or y equal to 0, this line is going to intersect the graph of this solution an infinite number of times. Here, for instance, and then here, and then here, and then here. And you will going to jump from a point to another by just multiply by 2x exponential 2 pi. This is the computation I've done here. So the second curve cannot be algebraic, because if it was algebraic, we would obtain two algebraic curves with an infinite number of intersections, which is not possible. The other solution cannot be algebraic. Okay, so this is not an answer, absolutely not an answer to the initial question of Poincaré. This is just to show you what should be an algebraic solution of a vector field and a non-algebraic solution of a vector field. I should mention that if you, for instance, pick randomly P and Q, this is a very hard theorem, but if you pick randomly P and Q, there is absolutely no algebraic solution to such a vector field. But this is a very hard theorem to prove. Okay. Let me just make a small, small remark here. Always, again, with that example, I can make the following remark. A vector field X, a vector field like I introduced in the very first definition, can be also viewed as a derivation on the space of a function, of polynomial function. So you can compute X of some function and using X as a derivation, and the formula, the general formula using the notation initially introduced, that would be just this formula. Okay, so here you didn't see exactly X as a geometric object, but an algebraic object, which would be just a derivation. X act here as a derivation. But of course, there is some link here. If I goes back to this example and I compute X of, if I compute X of the product of the two functions which define the algebraic solution, xy. So I'm going to compute this explicitly. So this is X xy plus ey d over dy xy. And so you find something which is written 1 times y xy. Or in another word, you find the function, the initial function multiplied by something. Let's say k times xy. And this is something which is very general, actually. This is an exercise. So the exercise is very general. If you apply x, so let's say now x is any vector field, as a derivative operator to some function, and if you do this computation, you finally fall into the ideal generated by this function, then exercise any level curve of, the zero level curve. If you look at the zero level curve of this function, it is an algebraic solution of the vector field. So this is just an exercise. Okay. You have to do some computation locally and so on, but this is not a very difficult exercise. Okay. This is a very, very general statement. Let me now give you a second example toward a negative answer to the initial question of Poincaré. So the second example is, again, a linear example. So I write, so let P and Q be two integers, and you look at this linear vector field. So again, this is a very, very simple situation. I get a linear vector field. P and Q are integers. And now if you take H equal to xpyq minus any number, where C is any complex number, you can show that X, if you apply to H X as a derivation, like here, then you will find actually 0. Which is, of course, something times H. You just have to make K equals 0. So actually, the 0 level of this function H is a solution of this vector field, and the 0 level of this function is actually the C level of this general function. H is what we called, for this very particular example, H is a first integral of X. So what is the picture here? So if I draw a picture in two real dimensions, but you have to imagine that here I have two C axes. The level of this function, you have two very special levels. If you look at the 0 level, it is just x and y equal to 0. So it's more or less like in the same example here. You have these two 0 level, which are solution. And then if you look at the C different from 0, this is a, well, algebraic curve, whatever, which looks like something like that. So if you draw the real picture, actually, of this vector field, this is exactly this picture. So here you have the 0 level, and now, and for C different from 0, you have the other level. Okay. So what I was about to say, okay, and yeah. Notice that in both examples, the 0, 0 point here is something quite special. In this example, if you see that if I plug x equal to 0 and y equal to 0 into the coordinates of the vector field, you get 0. Yeah?
There is some minus missing in the expression of...
Yeah, probably. Okay, thank you. Probably, yeah, you're right. This is a standard mistake. Yes, oh, I didn't make the mistake on my paper. So, okay. So this is, if you put x equal y to 0 in both coordinates of this vector field, and the same up here, the vector field equal to 0 this is what we call the singularity of the vector field. So here you see that this point somehow seems to be quite special for the vector field, and the same here. This point seems to be quite special, and this is what we call a singularity of the vector field. Okay. Okay, with that two example, I'm going now to show you how, a priori, it is very easy to give a positive answer. But it's going to be wrong, but it's very easy to give a positive answer to the question of Poincaré. So, how to give a positive answer to Poincaré problem. Well, you just have to do the following thing. Consider this vector space, so CK xy is the vector space, the finite dimensional vector space, C space of polynomial function of degree kk and so you can now consider the following linear map. So let me just, you can consider the following linear map. So you start with K and H that belongs to Cn minus y of xy times Cd of xy. And the range of this linear map is C n plus 1, n plus d minus 1 of xy. And the expression of this linear map is you look at x, which add as a derivation on the function h. So x is a vector field fixed initially, and then you remove k times h. Okay, so here n is chosen to be the maximum of degree of p, degree of q, where of course you can imagine x is p dx plus q dy. Okay, so you see that now if I found something in the kernel, if h, so let's give a name to this map, theta. If kh belong to the kernel of this linear map, then you see that h equal to 0 is an algebraic solution. So apparently the problem is solved. Because to compute a kernel with a computer, it's very easy. You have here a linear map. This is a matrix, and then this can be a very huge matrix. Okay, the computation can be very long, but at least it can be done with any computer, because you write down, you take any basis of this vector space, and you write down the matrix, and then you compute the kernel, and if the kernel is not 0, then you have Of course, h should not be a constant, but if you find in the kernel a non-constant function, then you have an algebraic solution. But here, of course, there is a very huge issue here, that is how to choose D. D would be, as you can see, the degree of the potential algebraic solution. So the question is, okay, you can make this computation, but how to a priori choose D? So basically, the initial problem of Poincaré can be stated in the following way. Given a vector field X, can we find an a priori bound for a potential algebraic solution? If we were able to have such a theorem, let's say a theorem that states, given X, if you know given a vector field X, for instance, if you know the degree of the vector field, you can compute n, for instance. Is there a way to find a function of n that give you the degree of algebraic solution if such algebraic solution exists? If there was such a result, then the problem of Poincaré would be solved. The problem is that with that example, you can see that this is impossible. Here, the degree of this vector field is 1. For this vector field, the integer n is 1. And you see that the degree of any algebraic solution here, of most algebraic solution, is p plus q. P plus q. And you can, of course, making p and q as big as you want. So there is no way to find an a priori bound for the degree of a potential algebraic solution for a vector field X once you know only the degree of the initial vector field. You have to know more. At least this example shows that the degree of the initial vector field is not enough to produce an a priori bound for this integer d. But of course, here you can, of course, Poincaré already knows this example. But here there is something which is not really fair, is that when p and q get bigger, you see that this integer get also bigger, and in some sense, the singularity here, the complexity, I'm not going to explain what I mean by complexity, but the complexity of this singularity is getting bigger and bigger. So it's not so surprising that if the complexity, if the degree stay equal to 1, but the complexity of the singularity is getting bigger and bigger, it's not necessarily surprising that the degree of the algebraic solution is getting also bigger and bigger. So the really question of Poincaré was, suppose that we have a vector field with eventually many singularities like that, many other points where the vector field equal to 0, and suppose that we control the complexity of each of these singularities. Then, can we find a bound for D? And the answer is still no. And this is a very famous example of a Brazilian mathematician, Alcides Lins Neto. So I'm going to give you the exact expression of this example. So this is due to Alcides Lins Neto, and it was published in 2002. And so Alcides produced the following example, which is now in the community, at least in the community, quite famous. So alpha being a complex number, you look at the vector field written this way, x3 minus 1 x dx plus y3 minus 1 y dy plus alpha times x3 minus y, y2 dx plus y3 minus 1 x squared dy. Okay, so this is a vector field. this is a family of vector field with a parameter alpha. You see that the degree is 4, the polynomial, sorry, 5. 5? Oh. This is a family. Oh, yeah, okay. This is, well, okay, 5, 4, whatever. The degree is bounded, okay? This is 4 or 5. It depends on what you call the degree, actually, but the degree is bounded. What does it look like? It's quite complicated, actually. You can see that if you look at the algebraic curve x equal to 1 or x equal to j, which is the third root of unity, or g square, these three straight lines are invariant. So you have the vector field look this way. You have three, sorry, x equal, so x equal, this is this way. X equal to 1, let's say j and g square. You have three lines like this, which are invariant. You could plug y equal to 1, j and j square, and this is the same. This is also algebraic solution of that vector field, so you have a line like that. And you have also, so of course these points are going to be quite special for the vector field. They are going to be singularities, actually. And you have also y equal x. You can see that if you put y equal x in this expression, you get also 0. I mean, if you put y minus x equals 0, then this is an algebraic invariant curve. Jx and j square x. All these straight lines are also invariant, so this is this way. Like that, they do not meet, so this is why I should write. This is a complex picture, so of course it is complicated too. These straight lines actually go through this point at some point. And this line here goes through this point. So you have, so these 9 lines are invariant for that vector field. These 9 lines intersect on 9 points here. And there is 3 more points at infinity. Of course, these 3 lines, which are parallel, they intersect at infinity. Like that also. And the 3 lines here, 1, 2, 3, intersect also at infinity. So you have 3 more points at infinity. Okay. So you have here 12 singularities. And if you zoom on any of these singularities, you will see a vector field which looks like this way. So to be more precise, if you zoom, if you look at locally what is the picture, on each of these singularities, locally, you will see a picture like that, which is associated to a vector field that is written this way. d over dx plus y d over dy. And this is true for the 12 singularity. And it doesn't depend on alpha. Of course, this description is true for any value of alpha. And actually, you have, to be perfectly honest, this vector field has 21 singularities, so there is 9 more singularities, which are somewhere. It's not clear where they are. There is one singularity, sorry, so one singularity, you have to add one singularity on each line. Here the singularities are a bit different, they are this way. Look like that, each of them. And locally, you have this picture. And actually, you can show that this is, there is this 3 that appeared. And this is what happened is that when you move alpha, the position of this point of this added singularity, 9 added singularity, moves. But still, if you look locally around the singularity, you get this this behavior. So my point is that you have a family of vector field parameterized by alpha, which is a complex number, with 21 singularities, but each of these singularities has more or less a complex type, which is very, very simple and bounded, which doesn't depend on alpha. But still, Linz-Netto proved that, the proof is quite difficult, but Linz-Netto proved that for an infinite number of value of alpha, x alpha has an algebraic solution whose degree is not bounded. Meaning that you can find some value alpha for which this foliation has another algebraic solution with degree 1 billion if you want. And what happens actually, this is my way to see things, that when alpha moves, what happened here is that in some sense this singularity are fixed, but the leaf around turn like that. And if you imagine that this 12 singularity turns like that, at some points, for some very special value of alpha, these little red curves are connected together. So you find a curve like that, which grows through all these singularities. And if you change the value of alpha, you get more and more and more complex curve. And so the degree is going to be more and more and more big. So here, this was a definitive, more or less a definitive answer to the problem of Poincaré, a negative answer. Even if you know a lot of information about the vector field, that is at least all the analytical type of its singularities, the degree and so on, many, many things about the vector field, still it is impossible to predict the degree of algebraic solution. So the answer to the initial question of Poincaré is no. There is no way to decide if a given vector field has an algebraic solution. Okay. I have 15 minutes, right? Yeah, okay, thank you. I don't want to finish on a negative answer. Well, this is negative in the sense that the answer is no, but this is a very famous problem and very, very incredible example, actually. But I don't want to finish on something which is negative, so let me speak now about the mirror problem. So the mirror problem is something which is studied for not a very long time. So the inverse problem Poincaré is my appellation. So this is not a standard appellation. But the problem is, in some sense, mirror, because the question is the following. So in Poincaré problem, you fix a vector field in the plane, and you ask is there or no algebraic solution. Can we decide, is there a degree that we can, is there a bound for the degree and so on? The answer is no. Okay, now you get it. So now do the mirror problem. So fix now a polynomial. So a polynomial, I'm going to keep the notation, so x, h of x and y. And now I'm going to allow myself to work not only in the complex field, but in any field. But keep in mind that if you want that k can be equal to c or any field. And the question is, what does it look like all the vector field for which H is an algebraic solution? try to say something. Let's say describe all the vector field X for which, and you can express H being a solution of X this way, for which X applied to H as a derivative, which is something which has a meaning even if K is any field, not necessarily the complex field, the real field or even a finite field, belongs to the ideal generated by H. So in literature, this set of vector field is denoted by this set is denoted by their derivation logarithm of X. This is not a notation, just a notation. The thing is that you can see that if you have there is a very, very simple remark. If you have an X that satisfies this property, you can multiply X by an element of this ring, by a polynomial, and still it is an element that satisfies this. Meaning that this set is not just a set, this is actually a module on the ring of polynomial function. This is a trivial remark. This set is a module on the ring K of xy. And now there is this result, which is a mix of many results, which is a priori known by the specialist, but not my community, and this is a very, very weird result. I'm going to try to explain why this is such a weird result. So this is a mix of some results which are due to Saito in, I think, in 80s, and a very hard result of Quillen and Suslin in the 78, I think, for which one of the two guys obtained the medal Fields, the Fields medal. Okay, the theorem is the following. This is a free. Meaning that it's free and of rank of rank 2. Meaning that you can obtain a very easy description of all the vector fields for which H is a solution just using two vector fields. This is rank 2. So this is just a sum of two rank 1 vector field, rank 1 module. And you can even, there is even a criterion for x1 and x2, two vector field being a basis of this module. A couple like that is a basis, meaning satisfy this equality. If and only if you take the determinant of these two vector fields, so you imagine that you take x1 and x2 are vector field on C2, with two variables on K2. So there are two coordinates, so you can put these two coordinates in a matrix and take the determinant of this 2 by 2 matrix. So you get, normally you get a polynomial function, but if and only if this determinant is delta time the initial, this is not x here, of course. It's h, it's dependent on the logarithm, on the function. Delta time h, where delta is just a non-vanishing constant. So delta belongs to the invertible. So this is a very, very surprising result. Why this is such a surprising result is that because you see here, imagine that x1 and x2 are just two unknown anything. This determinant here, it is a quadratic expression in these two. If you look at x1 and x2, the parameter of this vector field x1 and x2, the coefficient of x1 and x2 as parameter, this determinant is a quadratic expression in this parameter. So this equation here is a huge system of quadratic equation. These theorems state that there is a solution in the initial field. This is completely weird. I mean, normally, if you have a quadratic equation in any field, there is absolutely no reason for this quadratic equation to have a solution. X squared equal -1 has no solution in R. You have to take, for instance, the closure, the algebraic closure to get solution. But this theorem is true for any field, even if this field is not algebraically closed. So this is really, really, really weird. An explanation is that actually it is very, very difficult to compute these two vector fields. And for instance, the question would be, the mirror question of Poincaré would be, fix the degree of H. Can you find a priori a degree for x1, x2? The answer is yes. And this is a theorem which is due to a group of mathematicians known as Noai Fichas. This is a group of Spanish mathematicians. So this is not a real name, Noai Fichas. And apparently the story that when this group of mathematicians was working together in Spain, in Barcelona, I think, they often went to, at night, well, they went to a restaurant sometimes, and have to pick up some money at the machine, and the machines say, you can have the money, but there is no fiches, which means no paper that, probably during this week, whenever they went to a machine like that, the machine said, no fiches, no fiches. And so they decided to call themselves Noai Fichas. I think maybe this is this way. Okay, whatever. But what this theorem, so the theorem was much more general. But if you apply their construction in this situation, you can find that if D is the degree of H, and if H equals 0 is smooth, meaning you have no singular point along the curve, you have just a very nice curve, then the degree of x1, x2, yeah, let's say, okay, the maximum degree of x1, degree of x2 is bounded by a constant multiply d, okay, I'm going to write this, is bounded by a constant multiply d to the power of 4. So if you want to find a basis of this module, you can, well, let's say, look at the degree of h, and take x1 and x2 as unknown function, as unknown variables, but of d4, and then try to solve. And this d4 is very big, because in all my experiments, I never found such a huge boundary. When I tried, I make, of course, a lot of computation to find x1 and x2 in many, many, many situations. I always found something which is more or less equal to d squared and sometimes d squared minus epsilon. I mean, this d4 is not natural. It should be at most d squared and maybe even linear in d. But for now, it's a kind of mysterious. And this is this is one of my actual projects to try to understand much more this problem, to understand why this theorem works, even if K here is any field, to try to make this bound much, much lower. Okay, thank you for your attention.
Thank you very much.
Are there questions? Comments?
Just a rather stupid question.
Yeah.
The field can be finite too.
Yeah. You can, I mean, I was really, I mean, I spent a lot of hours making computation with F2. Oh yeah, there is a, this criterion as a, the characteristic of the field should not be, should be 0. Because if you are in positive characteristic, this is still true. I mean, if you are in positive characteristic, there are still a basis, but this criterion is no more true. In most situations, this is still true, but in very, very special, when H, for instance, if you imagine that if you are in characteristic 2, okay, and if you look at this curve, any derivation is going to be equal to 0. So there is something strange here. Okay, but still, if it's any derivation, you get all the derivation, and all the derivation it's a free module. Okay, so the theorem is true, but the characterization is no more true. So you can put here any field, and I made a lot of computation with F2 with singular and so on. And what is strange is that I never found such a high bound in this computation. And I'm pretty sure that this is because we have not the good. We do not understand really. This is a linear problem. And we abort this problem. We approach this problem with non-linear techniques. But this should be a linear problem.
Other questions? No, there are no questions from Montpellier and Perpignan, so I propose to stop here.
Thank you.
Thank you again for your nice talk.
With me.